Hey everybody, this is Dr. Ray, and in this video we are going to be exploring a third material properties example, which comes from a mechanics of materials list of topics or mechanics of materials class. So let's look at our given information. We are told that a cantilever support is made from a polymer material with a shear modulus of 1200 psi. And then we're told if the free end is loaded with a 120-pound force, compute the vertical displacement of the free end due to shearing effects, okay? And then we're also told that this cantilever support has a thickness of 1.5 inches and the material is behaving linear elastically. So let's take a look at a figure. All this is still given. So in a profile view, which is like looking at the side of this figure, we have a fixed connection here, and then we have this little cantilever support, or you could even think of it as like a little cantilever beam, and we have this vertical applied load here of 120 pounds, okay? Now, the length of this little cantilever support is 7 inches, and the depth is 6 inches, all right? Now, if we look at a cross-section view, what we're going to see is the 1.5-inch thickness along with the 6-inch depth. This 6-inch depth is the same as this 6 inches. So where is this cross-section in the profile view? Well, again, if you take a cut section through the profile view, what you will see inside of that cut section is this cross-section right here. Okay, so that's just kind of our given information and what we're looking at. So let's go ahead and write solution here. Now, the first thing I'm going to draw to get the process going is my deformed shape. Okay, let's look at a deformed shape. So I'm going to go ahead and redraw the original figure, which looks something like this. Here's the 120 pounds, okay? And of course, we've got a 7 inches here, and then we've got the 6 inches here. And then in red, I'm going to superimpose the deformed shape. Now, the problem clearly says calculate the vertical displacement due to shearing only. So when we draw this deformed shape, we're not looking at flexure. We're not looking at a deflection due to bending. We're looking for a vertical displacement due to shearing effects, okay? So because of that, what we can do is draw a displacement profile that looks something like this. This is what we have in red. So the vertical displacement that we're looking for is this dimension here. And it turns out this is the same dimension on the bottom side of this cantilever support, okay? Now, this angle that's generated, there's an angle that's generated that is related to this vertical displacement on both the top and the bottom surfaces. We'll call this angle gamma on both the top and the bottom surfaces. All right, so whenever we are dealing with shearing effect and the material is still behaving linear elastically, what we can then do is apply Hooke's law, okay? So what is Hooke's law for shearing effects? Well, if you remember that, it's tau equals G gamma. Tau is shear stress, G is shear modulus, which we know that, so we can kind of check that off. We know shear modulus, that was given to us in the problem statement. And then gamma is shear strain, okay? It's a shear strain value in radians, and that is the same gamma that we've drawn on our diagram here, okay? So that's Hooke's law. Now, the next thing we need to do is figure out how do we relate gamma to delta. Well, to do that, we can apply small angle theory, okay? So what does small angle theory tell us? Well, small angle theory basically says that the angle that you're interested in is going to be approximately equal to the tangent of that same angle, which is equal to, what's the definition of tangent of a right triangle? It's opposite over adjacent side, okay? So small angle theory says that when you have very, very small deformations, very teeny tiny deformations, what you can do is you can say an interior angle is approximately equal to just opposite over adjacent side, and then you can completely drop the tangent operator, okay? So that can save you some computational time and some computational headache depending on your given problem. So what we're gonna do, we're gonna apply small angle theory because in general, this is very small displacements and small rotations. So we're gonna say that in this little bitty right triangle here, okay, or this bottom one, you could look at either of these right triangles. We're going to say that the interior angle gamma is going to be equal to the opposite side of this little right triangle divided by the adjacent side, which we know is to be 7 inches. So we can say that little gamma is equal to little delta divided by 7 inches. Now we can substitute that into Hooke's law by saying tau equals G times little delta over 7 inches. Okay, now remember, we know G already. We know G. That was given to us in the problem statement. That was 1200 PSI. So we can make a note of this. This was given as 1200 PSI as it is given here, okay? So the next thing we need if we want to solve for little delta is we need tau. We need shear stress. Okay, so how do we get that? Well, look back at our diagrams, okay? What is being sheared here? Think about the material that's being sheared. Well, the cross-section area, this cross-section area is what is being sheared, okay? This 120 pounds is causing a slicing effect through this cross-section area, all right? So here's what we can kind of sketch. We can say here's our cross-section area, and of course it has a thickness of 1.5 inches and a depth of 6 inches, and this is the area that is being sheared, okay? So this is our shear area. And so what we can do is say tau, the shear stress, is force divided by area, but in this case it's our shearing area, right? So it's going to be the 120 pounds divided by 6 inches times 1.5 inches. And we can calculate that shear stress as, I'm going to use my calculator now, 120 divided by 6 times 1.5, and you get, or I get 13.33 PSI, pounds per square inch. So again, this 120 pound force is causing a slicing effect through this area that's 6 inches by 1.5 inches, and that's how we calculate that shear stress. So now we're basically ready to go to calculate the thing we're interested in. We're interested in delta. And of course, delta, if you rearrange this equation here, we'll get delta equals 7 inches times tau divided by G, okay? And so we'll say 7 inches times 13.33 PSI divided by G. And what was G again? I'm going to scroll back to the problem statement. G, the shear modulus, is 1200 PSI. So we're going to put the 1200 PSI in this denominator, and we will use our calculator to help us calculate this out. And we get a delta value of 0.0778 inches, okay? And you can see that it's inches because the PSI units cancel, and of course you're left with inches. So finally, your solution is delta equals 0.0778 inches. And that is the conclusion of this example video. Thanks for watching. Please hit like and subscribe.